For science today, we are doing a little bit more with Bernoulli's principle stuff that we started to do yesterday. So hopefully you have a page, like a double spread fold, I would say, of your science that you can continue working on today. We're going to be drawing more pictures to further explain some of the concepts behind Bernoulli's principle. And we're going to get into like how it works for flight too. So, okay, first of all, this should be submitted on Edmodo. Sorry, not Edmodo, on Seesaw, okay? I'm not gonna give Class Dojo points at this point because I'm making this video earlier than 1 o'clock for when I said it was due. But please do that. Maybe I'll give the Edmodo points at the end of the day in our, in like the agenda. So this is what you need to do, okay? So I've looked through some of them and some people, they haven't really done what I'd asked. Okay, so hypothesis, cool, write that in. Then what you needed to do was you had to draw what your observations are, okay? So maybe if I just like go into this, here, okay, right here. Okay, so hypothesis, write something down. Observation. So an observation, you need to draw something, okay? So label where the air is moving quickly and the associated pressure. So this is from the lesson from yesterday. So here you should draw the bridge again, but what it looks like, okay, when you blew underneath of it. So just do a quick little sketch. It shouldn't be too hard to like draw this little thing. And then say, okay, where's the air moving quickly? And then what is the pressure? And then you also could say where the air is moving slowly and what is the pressure. And then your conclusion, what's happening? Like, why has this happened? Whatever you have observed, okay? So please do that today. Okay, maybe even you need to pause this video and then do that and then come back and watch the rest. Okie dokie. So that is the first thing. And then now, today, we're gonna watch this. Okay, so Bernoulli's principle in action. Now this is super cool. There's a couple different experiments that are shown here, and this is pretty sweet. So I'd like you to sketch one of them. Okay, so here this is showing these like floating balls in Bernoulli's principle. It's pretty cool. I've always done this with a hairdryer and a ping pong ball, but he shows a couple different ways to do this too. So you can try out some of these experiments if you'd like to. I don't think you'd probably have like a smoke machine, this like leaf blower thing, but he shows the one at the beginning that you could do. So I would like you to sketch one of them, okay? And then it's optional if you'd actually like to do any of them. Okay, so we're not gonna watch the whole thing because it's like kind of long. Okay, here.
Can maybe enjoy them as well. To start off with the first one, all we need is a straw that's a little bit bendy and some ping pong balls.
Cool.
Ah! Let's go bigger. Ready?
This one you could do.
So what is Bernoulli's principle? Well, I'm gonna walk you through it as we do these experiments, but I'm gonna kind of play in between because really, like I said, I'm just experimenting so that I can discover and understand what it really means. What happens if we add a few more balls to this? I have no idea. Let's find out. But a very simplified definition of Bernoulli's principle is that faster moving air has a lower pressure.
Faster moving air, lower pressure, right? Fast moving air, low pressure.
I'm guessing this is overkill, but that's how we like to do things. Overkill, right? Ping pong ball and 110 mile an hour wind with the Black & Decker. Overkill. Let's take this off.
Okay. He does that for a while.
Is that the ball wobbles a bit. And that's because as the ball wobbles back and forth, it's the high pressure air, so that's the air that's not moving as fast, it's pushing it one direction and it falls back into that lower pressure air. And this happens back and forth. It oscillates and it gets stuck inside this oscillation of lower pressure and higher pressure air.
Okay, so basically, high pressure air is going up, right? Like high pressure air is going, High fast moving air is going here, which has low pressure. But then the high air pressure, because of the low speed, which is outside of it, right? Just normal air, is pushing in on the ball. So it's constantly doing this like oscillating thing. Okay, there's a few more.
And as you can see, lower pressure zone, and the airplane has to move faster.
All right.
It's an airplane flies. An airplane wing is designed such that the air that's flowing over the top of the wing has to move faster. If it has to move faster, it's at lower pressure. The wing gets pulled up into that lower pressure zone, and the airplane flies. That's the same reason that this ball isn't falling out of the sky. The air is pushing it up. It's trying to fall because of gravity, but it's getting pushed back and forth into this low pressure zone.
Okay.
I figured, hey, let's do a little smoke, and then maybe we can really see Bernoulli's principle in action. And it kind of worked. I mean, you can see the air flowing up around it, but I couldn't see everything I wanted to see. And another thing I kept getting fascinated with was this. If you've got fast enough moving air, it doesn't even have to be perfectly vertical. But I wanted to go even bigger. I wanted to really see this. So I got some rubber tubing. And then I started experimenting with different balls. What I landed with, what worked best, was a foosball. The reason I chose this tube was it fits right in my hose. Now, you're seeing one very small part of many, many, many days of experimentation to see if I could get this to work. I don't know why it was so challenging, but it was. And eventually, this was a huge victory. I think we got hours of video just to get to this point. Now, why does this matter? You can really see Bernoulli's principle in action with this. Look at the ball, oscillating back and forth. As it gets moved into the high pressure, it gets pushed back into the low pressure, and it just stays suspended.
High pressure, outside.
We can probably see it even better if I color the ball the same way as my inflatable ball that I used earlier. Look at this. This is Bernoulli's principle visualized by a floating ball. Now, earlier we used air, now we're using water, but both of them are fluids.
Cool.
Now, this might seem trivial to you, but this has actually taken a lot more work than you would have expected to get this ball to float in midair. And I think this models Bernoulli's principle beautifully. We can see it with our own eyes, see it moving around.
Okay.
We got a lot more going on over here at Field Science.
Okay, there. So again, right? It is low speed of air outside, but that has high pressure. So it's pushing in on the ball. The ball wants to fall down because of gravity, but then the fast moving liquid, air, fluid, right? Or water has fast moving has low pressure. And then the slow moving air outside has high air pressure, so it's pushing in. Okay, so hopefully that makes a little bit more sense. That was kind of a cool video. Okay, so now this is, I just actually want to talk about this in a couple more moments. Okay. Alrighty, okay. So now we're going to apply this to flight. So Bernoulli's principle, as the guy mentioned, is related to why an airplane's wing is designed as it is. And part of it, we're going to learn a little bit today about like how the design of the wing, it's called the airfoil of the wing, the design of it like this, is one component that allows the wing to be able to generate lift. There is a couple other things as well, but we're mainly going to talk about Bernoulli's principle today. Okay. So, first of all, the classic example of Bernoulli's principle involves airflow over an airplane wing. Okay, so air flows faster over the top of an airfoil than under the bottom, therefore making Bernoulli's principle relevant. So in this case, if we were to be, we're going to watch a video later that's going to show this a bit clearer, but basically when the air comes up like this, then it's kind of like on a water slide, right? It goes like, it's going to fly down really fast over top of the steep edge of the wing, which causes the air to move faster. And we know with fast moving air, there is low air pressure. So, and then with the low air pressure, the wing is being pressed by the high relative air pressure underneath, because this air isn't moving as fast. So same kind of thing with the ping pong ball that we just saw. The high pressure is pushing the object towards the pocket of lower air pressure. So that is why this design is like this for a wing. Okay, so again, according to Bernoulli, the faster flow over the top corresponds to lower pressure and provides lift to the wing. Okay, I know that's a lot to write down. That's really only like the full amount that you need to write down today. But I do also suggest that you draw this and maybe even kind of like label it. And you could even kind of draw some like fast, like these are like really fast moving particles of air, just like if you're on a really steep water slide. It's gonna go faster. Okay, you can pause me if you need to. I'm gonna keep going. All right, we're gonna watch one more video.
Shh. I've snuck into Minute Physics Studio to... that's better. Now, everyone knows that a wing generates lift due to its characteristic shape. Since air travels farther over the top of the wing, it must go faster than the air underneath so that both streams meet up simultaneously at the trailing edge.
Close.
And according to Bernoulli's principle, faster flowing air exerts less pressure than the slower air beneath the wing. This pressure difference creates an upward force, lift. Job done, right? Nope. This simple explanation taught in many textbooks and classrooms has obvious problems, like how could a plane fly upside down? Some planes, like the Wright brothers, had nearly flat wings, so presumably air would travel the same speed over both sides and there would be no lift.
True.
Plus, experiments show that air streams don't meet up at the back of the wing. Air over the top goes significantly faster, reaching the trailing edge first. So how does a wing actually generate lift? Well, the key is the wing must deflect air downwards. This can be achieved using asymmetric or cambered airfoils or by increasing the angle of attack. Air under the wing is deflected down, and by the Coanda effect, air above the wing is guided along its surface and down as well. Since the air is slowed and deflected down by the wing, it pushes the wing up and back, lift and drag. This is in accordance with Newton's third law of motion.
Okay, you don't really know all of this stuff.
If you can explain lift only using the deflection of air and Newton's laws, then the Bernoulli explanation must be completely wrong. Well, no. Air over the top of the wing does go faster than air beneath, creating a pressure difference that generates lift.
Yes.
Then this Newtonian explanation is unnecessary rubbish, and the original explanation was right. But that's not true either. The original explanation incorrectly assumed that air over and under the wing must reconnect at the trailing edge.
Yes.
And there was no mention of deflecting air down. Each explanation done correctly completely accounts for the lift generated by a wing.
Okay.
They're just two different ways of looking at the same thing. So next time someone brings up the standard misconception, you can tell them that explanation just doesn't fly.
Okay,
Accounts
so
for the lift generated by a wing.
Okay, so basically, there's two reasons why planes are able to fly due to the wings. So one is this one, Bernoulli's principle. Okay, so high air pressure with a slow wind underneath, and then the fast air movement creates low air pressure, which causes the wing to go up from the high air pressure, pushing into the pocket of low air pressure. So that's one reason, Bernoulli. And then the other thing that relates to the airfoil design is the deflection of the wind, right? So if the wind's bouncing here, then it's going to go psh, and it's going to push down, causing the airplane to lift up, even as you would even just do with like a paper airplane, right? You don't need Bernoulli's principle in a paper airplane to have lift. You can still do it just with like tossing the airplane simply in this direction. Okay, so okay. I don't know why this somehow is weird to get out of. Okay, there we go. Okay, so that is it for today. Okay, so the only thing that you really needed to write down was a page that I put before of Bernoulli's principle and then drawing that one, drawing the picture of drawing this. Okay, this is the most important slide, okay, to have the information written for, okay? And then hopefully the videos just provided a little bit more explanation for that. And then the other thing I wanted you to do is do a sketch of like one of these experiments with the balls. because it's kind of cool. Now, a couple other things for Bernoulli's principle, which is kind of neat, is if we had more time in class to do more experiments, we would. But there's a few other cool ones which you could practice on your own. So I'm just going to explain them to you. And maybe you can even think of your own as well. Now, okay, one definitely is with balloons. So if you had 2 balloons and suspended them from like hanging, if you had them sitting far apart, kind of like our pieces of paper, if you blew between the balloons, what do you think would happen to them? Kind of similar to our magnetic paper experiment from yesterday. They would fast moving air, low air pressure. The still air outside has high air pressure, which would push the balloons together. So you could try that. What's another one? Another one is even just with like you could try this with like 2 plastic bottles, or like light objects. And the reason why like the paper works well and the balloons work well is because they're suspended in air. But technically, if you had like 2 like water bottles that were light and then you blew hard enough through like a little gap in between them, they should also stick together. So you could try that and see if you can get it to work. And then the other cool example, which I always love sharing with students, is, okay, so you know when you're having a shower and this only works if you have a shower curtain. And you know how the shower curtain sometimes like sticks to you? That is because of Bernoulli's principle. So cool and mind-blowing, because the air or the fluid that's created because of the shower, right? It's moving fast, which causes, and so like the air is moving fast also beside like the stream of water. And then that causes the shower curtain to get pushed in because of the high air pressure outside, which is still. So that is why that happens, which is so cool. So next time that you're having a shower with shower curtain, then see if you notice that happening. And then you can explain to your parents or your siblings that the reason why that's happening is because of Bernoulli's principle. So cool. Yeah, okay, so that's it for today. If you wanted to try those things or even like draw some more pictures of what I just explained on your page of Bernoulli's principle to further explain this with labels of fast moving air, low air pressure, still air or relatively slower moving air is high air pressure, which is going to cause it to press into the area of the low air pressure, which is where the water is moving quickly. Okay, I hope that helps you understand this principle a little bit further. And tomorrow we are going to move on in science to do a little bit more, which is involving lift and airplanes to get into our flight. Okay, so please make sure that you have done the Bernoulli's bridge experiment or the lab and you posted that onto Seesaw. Okay, other than that, you're just taking notes for today. Okay, good work. And maybe you want to have fun trying some of these experiments out too.